All right, so let's have a review of the lecture 14. And this is what we have discussed before the spring break. So this is the last session for the CMOS inverter, and we talk about the power and energy. Next. So here for the power and energy, we have two categories. The first one is this active dynamic switching energy and power. So this is when the input signal is switching. Like your inverter, you have your input switching from 0 to 1 or 1 to 0. Then the inverter will charge and discharge because you have a load capacitor as output. So this charging and discharging essentially consumes the power. And this is active power formula. It equals to the load capacitance multiplied by the voltage supply, VDD squared, and then multiplied by the frequency. So you can also think this active power is due to the short circuit current from the power supply VDD to the ground. So it's the same thing. Later, as you see that the charging and discharging the cap is actually due to the current flowing from the power supply VDD to the ground. So then this is the first part of the energy or the power. And then the second part is the static power. So this is due to the off-state or the subthreshold leakage current. This happens when the input has no change. So for example, if the input signal stores at 0 or at 1 for a long time, so basically you are doing nothing, like the sleep mode of your cell phone. So if it does nothing, then the current can still flow from the power supply to the ground through the subthreshold leakage. This is what we discussed in the lecture 10. And then the current is coming from the power supply. So then the power static is the VDD times the off current, where we define the off current as the current at gate voltage 0, but the drain voltage VDD. So if you have any questions, you can unmute yourself and ask. So let's try this feature. So anyone can unmute yourself and then ask one random questions. So let's just try this feature maybe. So anyone can volunteer and ask one random question.
A question about the material so far, but how's your day been?
Okay, so it just okay. So this feature is good. So then, yeah, after you ask the question, and then if I answered your question and you think the answer is satisfied, then you can mute yourself again. Then we can move on. So then for the first part, this active power and energy. So here we consider, let's say, a clock half cycle, where for this inverter, where the input is switching from high to low, and then the output, of course, will switch from low to high with this kind of waveform. This is due to the RC delay, as we discussed before. So here, if you think about the power in this 1 to 0 transition in the input, and output is 0 to 1 transition. So this is a pull up the output from the 0 to VDD. So for pull up, we know that the PMOS is working. So here the NMOS is off because the input now switched to 0. So then NMOS, the threshold, the gate voltage smaller than threshold, then the NMOS is off. And then here we ignore the threshold, subthreshold current, so we think it's completely off. And then you can think this is open circuit. And then you can approximate the PMOS as a resistor with some resistance RP. So this is first order RC circuit. So essentially you are going to charge this cap from 0 to VDD. And then during this charging process, so the power supply is going to provide CVDD square energy, but only half of the energy is stored on this capacitor, and another half of this energy is consumed in this resistor as the heat, because you have current flow and Joule heating, and you have current and resistor, then you will have the Joule heating, then the heat energy you generated is this half CVDD square. So this is the energy you consumed, and another half of the energy, half VDD square, is temporarily stored on this capacitor. So this is half cycle of the clock. And then the next half cycle, so where the input is switching from 0 to 1 and output you need to discharge from VDD to ground. So if you have this discharge, then this is pull down, and we discussed before the pull down NMOS is working, so the PMOS here is off. So NMOS is working, so then this charges here will be discharged through the NMOS to the ground. And again, this is the RC circuit. And then eventually here this voltage goes to 0. That means there's no charge on this cap. That means no energy stored on the cap. So all the energy you previously stored on this cap, like this half VDD square, will be consumed through this discharge current. Again, this energy is consumed as heat on this resistor. So you consume another half CVDD square energy in the next second half of the cycle. So in total, right? So here you see that half cycle, each consumed half CVDD square. One is NMOS consumed, the other one is PMOS consumed. So in total of one clock cycle, you will consume CVDD square. And then this is the energy, and energy and relationship between energy and power will be energy times the clock frequency. And this energy consumed in each cycle is a constant. It just depends on the capacitance, which is the load, and then the power supply, VDD squared. And clock frequency is what you can tune as a designer. If you run your clock faster, then you are going to consume more active power. So this is the active power and energy. And the energy is energy you finish some task, and then the power is the average power during this clock cycle. And then the second part is this static power. So this one is when the input stays at 1 or stays at 0. So no switching happens. But even the input stay at, for example, 1, which means VDD. So then this, for example, then if input is VDD, then the PMOS is off. Because here the VGS for the PMOS is 0. PMOS is off. However, if we consider the bias condition of this PMOS, you will see that the PMOS VGS is 0, but the VDS is VDD, because here this output is 0 and this node is VDD. So between the source and the drain, you have VDS, like VDD. So this is exactly this I-off current in the subthreshold plot, where you have the drain current as a function of the gate voltage, and this is off current when the VDS equals to VDD. So this is condition to get the I-off, and this is pretty small, like you may have nanoampere per transistor. So you have this current. This current comes from the power supply VDD. So then the static power is this VDD times I-off. It may be very small for each inverter, maybe a nanoampere, but you have like billions of transistor on the processor. So in total, it will be a remarkable power consumption, even if you are doing nothing. So if you have 1 million of this kind of circuits on chip, then 1 nanoamp will give you 1 milliwatt power. So still it consumes the power. So this is the static power. And then a few more words on the short circuit current. So this one is for the dynamic power. And then when you are switching the inverter, let's say your input is switching from 0 to 1, then you will notice that in the VTC curve, this is the VTC voltage transfer curve, the output will switch from high to low. And during this switching, in the middle, where you have the Vi, which you define the input equals to the output, then at this Vi point, you will notice that both NMOS and PMOS are in the saturation. So they are fully turned on. Then you will reach the largest current. You reach the largest current in this branch. So this is the peak current. And in this match the CMOS case, match the inverter, you will get this peak current as this equation shows you. Because for the matched case, you know the Vi, this Vm point, which is the middle voltage, will be half VDD. And you can plug in that to this equation, you get the peak current. So this is the short circuit current. Essentially, you have the current flow from the VDD to the ground, and this consumes the dynamic energy, dynamic power, because this is like the short circuit current from the power supply to the ground, and this contributes to the Joule heating, as we discussed earlier. So this is a quick summary. And for dynamic or active power, then we have this alpha F C VDD square. So here we add this coefficient alpha to represent the switching activity, because not every clock cycle you are going to have the flipping of your input. So only at certain cycles you will flip the input from 1 to 0 or 0 to 1. Then the percentage of the switching among all the cycles is represented as this alpha, that's the switching activity. So then you will have this coefficient in front of this dynamic power. And for the static power, then you will just have this VDD times the I-off. So this is for one inverter, total power dissipation, dynamic and static. So for the delay, if you use average current method, then the average current is mostly determined by the on-state current. So this C VDD divided by I on, you will see that if you want to decrease the delay, then you want to increase the on-state current. So one way to do that is to increase W over L of your transistor. So that's the quick summary of this lecture 14. So let's just use this as a practice. I will stop the recording. Later I will post this clip to the YouTube.